So I will talk on this self-organization and the flow of information within some confined active system. And now, so first the self-organization. Okay, so I'll go briefly here. That so there are pretty many examples of active systems, active particles, ants, penguins, and then active colloids, and then they all, it's a common property, they all self-organize. Okay, for various purposes, maybe foraging, maybe making this this so they do this self-organized, they do form this self-organized structure. So our first thing is how to control their self-organization. So the one way to do this is trapping, like trap them and then tune the trap so that we can organize them. We can tune the organization. Okay. So this is the one cartoon that we did in the sorry. So the detail is this in the paper. So what we do is like, so there is this kind of active particles, they are self-propelling and they are following their neighbors like Vichek algorithm. And then they have this repulsive interparticle interaction like WCA or Lennard-Jones kind of thing. We took many of them and then trap in a circular trap. Okay, and what we do, so the trap, the strength of the trap wall, they can be tuned. They can be made soft or hard. Okay, so this can be done in the colloidal system by laser trapping. So using the laser intensity, varying the laser intensity. So if we take the hard trap, and then the organization is like the particles, they go to the boundary, stays there, and they form like this disorders thing and this kind of weighted layer there. Okay, now we see that if we make the trap softer like here, so we do see two changes. One is these organization, they form a round cluster almost, so like a weighting. So this is a weighted layer, it's a deweighted. So waiting to do a deweighting transition. On top of that, if we look the organization inside this cluster, we see a nice hexagonal close pack. Okay, so these two things happens, and why the kinetics of this thing is detailed in this paper. Now, so that means that we can trap first of all, and then we can tune the trap so that we can tune the self-organization of the particles. Okay. Now, so this is the thing that is what is happening here. So this red color is the hexatic, local hexatic order parameter, which was very less in this, and we make the trap softer and softer, and then we get finally this hexatic cluster, round cluster. And we calculate the phase diagram of that. So this is the x-axis is the hardness of the boundary, y-axis is the Peclet, okay, the activity of the particles, and we find this ordered region. Then this is liquid-like disorder, and then this is gas-like disordered region. Okay, and this all calculations are in 2D. So this is the model that we are discussing. So this is particles are obeying Lajba kind of dynamics. This is the active force. This is the trapping and interparticle repulsion, WCA. This is the Stokes drag. And then we have some thermal noise. Thermal because we think of some colloidal system. And then we have the trap here, the tan hyperbolic trap, and then we have this Q is as a stiffness parameter. So if we increase Q, then the trap becomes more stiff, more hard, and if we reduce Q, then it becomes softer. So this is the model. And then, so given this context of self-organization, we try to measure the flow of information. Okay, so how? So first we did an experiment in silico. The experiment is like quenching experiment. So what we did, we took the trap to be very soft so that we can have a round ordered cluster, and we suddenly make this trap very hard. Okay, so do we do so what happens if we do that? So this is the video, I think it should play. So this is the color is the hexatic order parameter, local hexatic order parameter. It breaks, okay, and then we see a lot of changes, a lot of rearrangement happening. The order goes down, the polar order goes down, the hexatic order goes down, okay. And then I ask that these three questions. So we are like this. So first is, how are the flocking particles are informed about the quench? Okay, so we need the quantification of information first. Second, if there is information, then how this information flows over time and length scale, okay, and how this information flow time and length scales compared with the structural relaxation. So there are, due to the quench, the structural relaxation is happening, right? So there is some certain length scale and time scale there. So how these two length scale, the information flow time and length scale and this structural length scale comparatively, how they match, okay, or is there any match at all? So first step is to quantify the information. So this quantity in the information thermodynamics literature is called transfer entropy. Okay? What it is? So this is actually, so say this is the particle, I'd say ith particle. Okay, in the literature they say it is focal particle. So these are their neighbors. Okay? Now some information is transferred from J to I, similarly from this to this, this to this, and this to this at the same time point. So this fellow gathers all the information from its neighbor, then they sum up, okay, and then get the average information from their neighbors. Okay? And this information is quantified by this quantity. Okay? So the n is the time index. So it moves according to its previous configuration, its own and its neighbors. Okay, and then sum over all neighbors, so that I can get per particle transfer entropy. That means per particle information that I obtain from my neighbor at certain point of time. And this k and l, these index cares about the history. Okay, so if I go along the time arrow, then they are the history of this focal particle, and these are the history of any of the neighbor particles. Okay, so this quantity actually, this quantity actually takes care about the history of the system itself, okay, the particle itself and the neighbor also. And this is proposed, this is said that information transfer from one individual to other individual. It is almost like a mutual information, but it takes care about the history of the particle itself and the neighbors itself. And this is proposed in this paper in 2000. So now we can compute. So it is difficult to analytically, at least for the system that I am considering.
4 minutes are left. 4 minutes.
Okay, fine. So this quantity I can compute in my system now. So what I see? So this I compute and I paint my particles with this quantity. You will see suddenly there is a shock-like movement when it encounters the boundary. Then this you will notice. So this kind of shock-like movement is there, which starts from the boundary, ends at the flock. Okay, so this is like here. So this is where the encounter with the boundary starts, and then it moves, and then it forms a kind of a wave front there. So the natural question is, what is the length scale of this wave? That is the length scale of the information flow. And what is the time scale? What is the time it took from going from here to here? Okay. So this time length and time scale. So length scale is very obvious. It is like almost like a flock, the linear size of the flock itself. Okay. And what is the time scale? Time scale, for time scale measurement, so there may be multiple ways to evaluate it. What we do, we just distribute this transfer entropy over the particles, and before the collision with the boundary, we don't see any large tail behavior, but during the encounter of the boundary, it produces a large tail. Okay, so it is largely deviated value of transfer entropy is produced during the encounter of the boundary, and then we calculate, and this disappears when the front moves away from the flock. Okay, so this area that is the number of particles, the fraction of the number of particles that carries the large value of largely deviated value of transfer entropy is the measure of the time evolution. So we can calculate this area over time, and it shows a very large peak during the information propagation. So this is the time scale of this clock
2 minutes.
propagation. And on top of that, we see that this is linear. So the information propagates ballistically also. So directly jumping to the conclusion here is this, that the flow of information is quantified by the per particle transfer entropy, and this length scale of the flow is almost the flux size. The information flow is much faster than the structural relaxation time scale, what I find here in this system, and information flow is ballistic in time. So that's what the conclusions are. So I finish.